you're going to see questions being different regardless. Right? That's part of a learning process, to see how different questions in different formats and being able to still come to the answer. But as a pseudo way to address that, what we'll go through and do, because I went through and checked and verified that I'm fine with this, what I will go through and do is give you the opportunity to get half of those points back. So if you missed, say you got an 80, that means you missed 20 points. I will give you the opportunity to get 10 points back, which does jump the average. So I went through and assumed that everybody went through and did that, which you should. If everybody goes through and does that, the average jumps up to like 83%. Right? So it does make a significant difference in the overall rate. Before I was going to talk about that, I was actually going to ask one quick question. How many of you have been happy with your exam grades? 2 people. Right. How many people have actually looked at your old exam? Right, that's a little bit better. How many of you actually looked at the wrong answers on the old exam? Fewer. Why would you spend any time looking at the wrong answers? And I'm not saying the wrong, what you got wrong. I'm saying the wrong answers on the multiple choice. Anybody actually look at those? Why not? Good thought might be they're wrong. And when you get a multiple choice exam, 3/4 of that exam, it's actually more than 3/4, 80% of that exam is what? Wrong. Right? Odds are you will get answers wrong if you don't know what a wrong answer is. How do you know what the wrong answer is? There's 2 approaches. Okay. One approach is you know what the correct answer is. Okay. Odds that you know the correct answer, if you worked really, really hard, you should probably pick up most of the correct answers. But there's another way you could go through and do it. If you can identify wrong answers, you drop the number of wrong answers on your exam that you could potentially answer from 80% to maybe 50%. That's going to improve your odds of getting a correct guess on the exam. So one of the things that I'm going to offer is for you to go through within exam 3, and so you get half of your missed multiple choice points back, which is a pretty sizable amount of points. For each question that you got wrong, you need to explain why your answer was wrong. Okay? Or explain why the wrong answers were wrong on the multiple choice. We'll talk about what that means in a second. Or fully explain why a correct answer is correct. And I have to give you both options, because at least in general chemistry, there are some wrong answers that are so out of left field you'd have no idea where they came from. Okay? So if you can fully explain why everything is correct about the correct answer, then I can accept that. Okay? So what do I mean? We've got 3 example questions up here that we could take a look at. We want to discuss as far as how you would get points back for these. If we take a look at that first one, could you explain why all of those answers were wrong, or why 4 of those answers were wrong? To explain why it's wrong, you should know where that number came from. How could you figure out where that number came from? Any guesses? Think like an instructor and go through, look at the correct answer and say, what are the different permutations of how we could multiply and divide these numbers through to generate each of those. That could be a bit tedious to figure out the exact reasons why those numbers showed up. So in that first case, what I would expect you to do is to thoroughly explain to me how you get the correct answer. All right. So nice and clean, lots of work to explain how everything went through. Right, so you would show your work, you'd do all the explanations for what's happening at each of those stages. How do we convert one number to another? Where do we get the mass amount for? All of that fun stuff. All right, so if you got the answer right, you don't have to worry about it. But if you got that answer wrong, you just go through and you show the complete, detailed, beautiful work on exactly where that came from. All right? It's a lot of work to go through and process. For that one down below, going to be another situation of explaining why your correct answer is correct. Okay, this one doesn't involve any math, or minimal amount of math, so I'm more willing to actually work this one out for you. How could we explain that your answer is correct? Okay, so the first thing you should go through and do is provide the Lewis structure for NH3. So you'd show me all the work for that, your valence electrons, okay, which was step 1. You tell me what step 2 was in your rules. End up with nitrogen, hydrogen, hydrogen, hydrogen with the electrons. Okay. Does that drawing tell us what the correct answer is? No. Okay. That drawing gives us 2 answers. That drawing gives us trigonal pyramidal, and it gives us tetrahedral. Which is the correct answer? It's trigonal pyramidal. How do we know that? It asks for the molecular geometry. So what extra piece of information would I expect in an explanation of why it's trigonal pyramidal?
This is molecular.
I want a definition of your molecular geometry. What is that? Okay, and on the exam, what should you have underlined and circled? Probably molecular geometry, and described what that means. Because if you know what it means, then you can answer the question. If you read this question, you have no idea what molecular geometry means. Does it matter that you know how to draw the Lewis structure? It's completely irrelevant. So you need to be adding that extra information. That's what I want you to go through and do when you rework the question. Okay? How about that last one? Which of the following is an example of a chemical property? How many of you know what malleability means? Okay, we've got to stretch or disfigure the shape without fracturing anything. So what I would expect for this question is you provide the definition for every single word. Okay? If you've not done this with your old exams, for any of the questions you got wrong, the only reason why I would say you have not done this is because your average on the old exams is higher than 90%. Okay? If your exam score is lower than 90% on any of the exams, okay, and this goes not just for this class, for all classes, you need to go through and evaluate each of those answers and say, okay, why did I miss this question? What were the other possible multiple choice things? What things can I learn from those mistakes? Because remember, what did we say at the beginning of the semester that science was all about? Failure. Okay? And not just failing, but trying to change something about that process. So understand the failure, rework, and try and go through and do it again. It becomes super, super relevant for our class. Any ideas why? The final exam covers what material? Everything. So if you haven't gone back and learned from your mistakes, what's going to happen when you get to the final? You make the exact same mistakes, and you end up with, at best, the exact same score that you had on all your other exams. Okay? That's not where I want you to be. So as a process of trying to encourage you to go back and look at the exams and look at the material and review, that's what exam 3 is going to be for. So I'm going to give everybody the opportunity to do this. This is not extra credit, strictly speaking. Okay? You are getting points added back to your exam. If you are the one person that does not do this, let's say your exam, so we look back at our average was 65%. You got a 75% on the exam. You're happy with that, 10% above the average. You're the one person that doesn't go back and do this. What happens to your score? Stays the same, but the average, remember what we just talked about, jumps to 85%. Your score, instead of being 10% above average, is actually 10% below average. Okay? So it will, excuse me, it will hurt you if you do not go through and do this. That said, if everybody doesn't go through and do it, then it's not going to hurt you. Okay? So please go back and review your exams. There's something in there. Yes, question. Is our conversion factors. Right? So when we look at an individual conversion, there's really two pieces to it. Our units have two pieces. We have our standard measurement, so grams, moles, atoms, okay, all of that information. But when we move to chemistry, we add an extra piece to that unit. That extra piece is grams, moles of what? Okay? So when we think about our units, it's two pieces, a measurement and our substance. What is that substance? How can we connect it? All right? So when we look at those individual conversion factors, you need to be able to find, and that's one of the things that we're testing you on, you need to be able to find these conversion factors. When it comes to homework, it's nice. You can use the textbook. You can use the textbook to find that conversion factor. When it comes to the exam, there's really only two things that you can use. Either the exam gives that information to you, or you have to process it through your brain. You've got it memorized. Or you have to interpret it off of something else. Once you know those conversion factors, you can then organize them in some fashion to allow you to convert between individual units. The method that we've talked about in this class is dimensional analysis. Numerators, denominators, to get your units to go through and cancel. Right? So what we've got written there along the bottom is how we can potentially convert between each of those units and where those conversion factors are found. So when we think about exam 3, we could look at our atoms as a particular unit. So atoms of A. If I want to convert the atoms of A into some other unit, say into atomic mass units, okay, I need to have some place to find that information, to change that unit. Where is that unit found, or that conversion factor found? Well, that comes off of our periodic table. Okay, so you'd have to look to the periodic table. Are you given a periodic table? Yes. Yeah. So you don't have to think about it. You don't have to memorize that number. You just have to know that to do that conversion, you have to use the periodic table. Okay? And the numbers given to us on our periodic table, say for hafnium, we have 72 and 178. What is 72? Okay, it's our atomic number, which represents what? The number of protons. And in its neutral state, the number of electrons. What's the 178 represent? It's the atomic mass. Well, if I'm trying to convert the number of atoms into AMUs, a mass unit, what is this number?
The number of protons and neutrons.
Yeah? It's the mass in atomic mass units per one atom. Okay? That conversion factor is awful. It's valid, but we typically don't use that. Why not? When you run a reaction, how many atoms do you use? A lot more than one, which is why we invented a new conversion or a new unit to use, which was Avogadro's number, the amount of atoms per mole. Right? So if we want to now interpret going up to a larger scale, going, say, from atomic mass units into, say, grams, something that we can actually weigh, we've got a new conversion factor. That's AMUs into grams. And we've got this random number. Does that number look familiar to anybody? Okay, it may not. But if we switch this around and say, let's do 1 divided by that number, 10 to the minus 24. Anybody know what that number is? I'm really good at math, so let me approximate this. So 1 divided by 1.661 is approximately 6.022. And 1 over 10 to the minus 24 is approximately 10 to the 23rd. It's Avogadro's number. The relationship between AMUs and grams is Avogadro's number. Okay? So we have seen that number before. It's just in a slightly odd format. Okay? So that can allow us to go from grams to moles. Again, if we're never in AMUs, right, if we never start in AMUs, do we need Avogadro's number? No, because Avogadro's number goes from AMU to grams. If we're in grams, do we need to worry about it? Nope. When do we need to worry about it? If I go to AMUs or atoms and molecules. It's the only time it matters. Okay? Once I'm in grams, can I convert that into moles? Yep. Where's that information found? No, this isn't Avogadro's number. It's also found on the periodic table. That exact same number of 178 for hafnium, okay, is our AMU per atom. But if we now scale this up and look at 6.022 times 10 to the 23rd atoms, what do we have to do to the mass? To scale that accordingly as well. Okay? And if we leave that in AMUs, we'd get this big, massive number for AMUs. But what can we do with the AMUs? Convert them back into grams, and what happens to our number? What's the relationship between grams and moles for hafnium? 178 grams is 1 mole of hafnium. So our atomic mass we can use as a molar mass just as easily. So that information is also found on the periodic table. What happens in our next step? We're now moving from moles of A. Where'd it go? Whoops, it's over here. Moles of A to moles of B. Okay, so I've got moles and moles, so we might say, oh, the units are the same, so it's the same number. Are the units the same? The measurement's the same, but is the substance. I'm converting from substance A to substance B. To do that conversion, I have to know a relationship between those two. Where can I find the relationship between those two? All right, there's a few places. If I gave you, say, the formula sodium hydroxide, what is the relationship between sodium and oxygen in sodium hydroxide? How do you know it's 1-to-1? We look at the subscripts, and we have an implied 1 for both of those. So if I want to convert the moles of sodium into the moles of oxygen found in sodium hydroxide, I now have that conversion factor. It's 1-to-1. Does it have to be 1-to-1? No, because I could change this formula now to be, let's pick sodium sulfate. Is it 1-to-1 now between sodium and oxygen? No, now the numbers have changed. We would then incorporate that into our conversion factors. What if I want to find the relationship between reactants and products? Can I use a formula for that? What's the product in sodium sulfate? Should be kind of a hard question. Or the reactant. Either one. Take your shot. What's the reactant in sodium sulfate? Product? There's no reaction. Sodium sulfate is a formula. There's nothing to react. I'm not reacting with anything else, so I can't show a relationship to anything else. Where do I find the relationship between reactants and products? In a reaction equation. And in particular, that conversion between those comes out of the balanced reaction equation. So we'd have to look at the numbers in front of each of the units that we're referencing. Okay? So it's a question of where do we find this information? And almost always it's given to you, either from the periodic table, okay, or from a balanced reaction. The one that we typically don't give to you because we've decided it's so uber important that everybody has to memorize it is Avogadro's number. Okay? It's a bit silly, but that's the way it works. Okay? Questions on that? Okay? So another way to change and format how we could find these things. Okay? Measurements. Tables of them are in your book. So to convert individual units, we've got access to that. Okay? So we can do those conversions. You're supposed to have memorized the metric conversions. Okay? The English conversions are provided to you. We don't expect you to memorize those because English is such a hard language, we don't barely speak it. We don't want to worry about dealing with the unit conversions. And that was supposed to be a joke. I'm glad you guys are so happy. The number of atoms. Okay, we can convert between different types of atoms from a formula, but we have to make sure our formula is balanced. What's the relationship of magnesium to chloride in magnesium chloride? 1 to 2. But if you're given the name magnesium chloride and asked for that relationship, what are you expected to do? For instance, let's switch this up and say, what's the relationship between magnesium and bromide in the compound magnesium bromide? There's a nice little question. What's our conversion factor between those? What's the first thing you have to go through and do? Get a formula. So we have magnesium and we have bromide. Is that formula balanced? No. Why not? Magnesium's a +2, bromide's a -1. Our charges don't balance. So what do we have to do? 2 bromides. Now what's the relationship between magnesium and bromide? 1 to 2. Right? So we need the balanced formula before we can move forward. If we just make up some random symbols, we can't actually apply that. Same thing happens when we look at our number of molecules in a balanced equation. Okay? Our equation's really nice because now I can convert one reactant to another reactant. What's the relationship between the amount of tin +2 in comparison to the amount of iron +3 that I need? 1 to 2. How do you know that? It's the coefficients. Now, it's the numbers in front. So if we're looking at a balanced formula, we end up looking at our subscripts. If we look at a balanced equation, we look at our coefficients. And our equation's even cooler because we can now also relate it to the amount of product produced. Okay, what's our end result? How much can we get out of the end of our experiment? We can look at our numbers of moles. We can convert atoms into molecules. We can also convert formulas into molecules if we wanted. Okay? Or formulas into moles. So we've got a way to do those individual conversions based on that magic number, 6.022 times 10 to the 23rd. Okay? And then our atomic or molar mass, that information is given off our periodic table. Okay? You are responsible for both. Whoops. It's not grams per atom on the periodic table. It's AMUs per atom. Okay? That information is there. You just have to look and find it there and realize that that's where it is. Okay? So, chemistry is providing a rule set. You have new rules, and you now just have to apply those rules again and again and again. Okay? As fun as that might be. Okay? So we've got some general instructions. You then have to apply those instructions to what's happening within this class. What do you do in your everyday life? Are you given a rule set? What does a red light mean?
Stop.
That's a rule. Do you follow that rule?
Yeah.
Okay. Typically. Okay. Maybe sometimes there's some other extenuating circumstance that allows you to say, well, I'm going to skip the red light being a stop sign now. Okay. You are interpreting rules every day. Chemistry is now giving you a new set of rules and allowing you to then apply those rules within the context of the class. When you step out of the classroom, you're still doing this. You're just not using the rules that chemistry gave you. You're using the rules that we give you, okay, or that the government gives you, okay, or your friends give you. For instance, is it considered proper if you walked up to your friend and just slapped them across the face? Probably not. Okay, maybe some people accept that. Okay, but it's usually frowned upon. There's a rule that you're following and knowing to not do. Same thing's happening within chemistry. So we've got these new units on which you have to manipulate. So figure out the rules. Once you've got the rules, it's just applying those rules again and again and again. Okay? So here's a fun little question. Oh, I don't like this question. Oh, no, let's switch it up. Let's do the easy one first. Go ahead and take a swing at this one. Talk to the people around you. Figure out what's going on with this. So our ultimate goal is, what does Harry have to do to get his pennies converted into dollar bills? Right? And how many dollar bills can he get? So we'll work through. So Harry's got 100 pennies. He wants them as dollars. How many dollars could he get for that? $1. How do you know that? You know that 100 pennies equals $1. So if we use the conversion factor, 100 pennies, we will put pennies on the bottom because units need to cancel. Equals what? $1. What's that equal? I am throwing it. It's $1. So we would expect Harry to get $1 out of this. Not a bad deal, except what's Harry's problem? Who has dollars? Douglas does, but he does not like anything other than silver. So if Harry tries to take his 100 pennies to Douglas, what happens? Throws pennies back in Harry's face. So Harry's got to find some way around this to get his dollar. So what does he do? Because he can't convert 100 pennies to $1. He goes to Sally, and he takes his 100 pennies. Okay, and what's our conversion factor between pennies and dimes? 10 pennies equals 1 dime. Look at our conversion. Where do pennies need to show up? On the bottom. 10 pennies is 1 dime. He now has a bunch of silver dimes. We could look at that number, but does Harry really care about the number of dimes he has? No. So if he doesn't care, let's not bother to calculate how many dimes he has. Okay, let's assume that Sally's an honest person. Okay. Now what happens? Now that he's got his silver things, what does he do? He goes back to Douglas and says, okay, Douglas, I want some dollars. But now he's got dimes. How can he convert dimes into dollars? 10 dimes is $1. We go back to our setup. 10 dimes, $1. What's the result? We get $1. And he's gone through and set up this conversion. You see this type of thing in math all the time, right? These weird equations, 2 buses traveling opposite distances, cross cities, and what time, all that speed junk. You wonder, why the heck do we have these types of questions? Okay, we have these types of questions because what we're trying to do is get this into a real world where you can visualize and see this. Did I tell you that 100 pennies equals $1? I didn't tell you that. You knew it already. In chemistry, I tell you a conversion factor. What do I expect you to do with that conversion factor? You need to use it to apply and convert those units. You do this kind of calculation every day. You've just internalized it because the numbers we work with in our everyday life happen to be relatively easy to manipulate. We can deal with tens and hundreds. Okay? We can understand those relationships. But what happens if we change those numbers into something crazy that we don't understand? We look at billions of numbers. Well, now it's confusing. Right? You'd still probably be able to figure it out. But what happens when we move into chemistry and we say, okay, let's change the numbers, and instead of it being a nice unit that you like and understand, I'm going to convert now Snorlaxes, Skittle Farts, and dimes. How do you do that conversion? Now everybody throws up their hands and freaks out and says, oh, that's the end of the world, I can't deal with this anymore. Okay? Except what do we give you in the textbook? We tell you that 10 Snorlaxes equals 10 dimes. Okay? We tell you on the exam that 10 dimes equals 1 Skittle Fart. You have those conversion factors. But what you have to now do is take it out of your head and put it onto paper. We do the exact same process. So let's try it again. Harry wants to exchange his Snorlaxes for Skittle Farts. And apparently, Snorlaxes aren't silver, in case you didn't know that. Okay? So how does he go through and do this process? Well, if he's got 100 Snorlaxes, I can't believe I'm actually saying this with a straight face. Maybe it helps that you guys are so tired. We've got 100 Snorlaxi that he can't convert with Douglas right away. So what does he have to do? We have to convert them into dimes. All right, well, how do we convert them into dimes? What unit needs to show up on top? Dimes. What unit needs to show up on the bottom? Thank you for saying that out for me. All right, what's the relationship between dimes and Snorlaxi? How do you know that? We look at the conversion factor that we were either memorized or is in our textbook or is on the exam. We now can do that conversion into dimes, but we don't want dimes, we want skittle farts. How can we convert dimes into skittle farts? We want to get rid of dimes and we want the skittle farts to come back. You guys are really not laughing at this. This worked so much better last semester. Do we have a relationship between dimes and skittle farts? 10 dimes is 1 skittle fart. Okay? Come on. Give me something. We can now go through and set up our conversion. And we can figure out exactly how much skittle farts that Harry can get out of this. Well, you aren't going to laugh, I got it. Okay? This is what chemistry is. We've given you crazy units. You now just have to manipulate those units within the system that you already know. You do this every day. Okay? You just have to find and be aware of where those conversions are found. Well, where are all those conversions found? We've got a list of where they're all found. How do you know that you should be finding them there? Practice. Okay? Or you can memorize where each of those conversions are found so that when you get to the exam, you can look immediately at that place. Should you ever memorize that tin plus 2 is going to turn into 2 iron plus 2s? Why not? Because if I change this to gold, does that get me iron plus 2? No. So we're not memorizing the exact relationship. We're memorizing where to find that relationship. Kind of, sort of? Okay. So let's take a look at some formula usage. To go ahead and build a wheel, what do we need? You need spokes and you need a rim. Okay, so what's our formula for the wheel shown? Yes, I'm expecting you to count. Did you really count it that fast? Okay, fine. I didn't bother counting. Okay, so we have, assuming that people count faster than I do, 24 spokes and 1 rim. It's that one that was throwing me for a loop. We could go through and write it out like this, but maybe we want to come up with an abbreviation. Okay? Some way to organize this so that we can quickly reference how many pieces went into this. So what we might come up with and say is that our spokes will be the symbol SP, and that our rims will be the symbol R. I can now organize this into saying RSP with 24. I now know what a wheel looks like. This equals 1 wheel. Okay? Chemistry is doing the same thing. We're taking these terms and we're now trying to condense them into a formula so that we don't have to write out spokes and rims. We can write down the abbreviated symbols for them. All right, well, what would we do with a wheel? Who cares if I've got a molecule? Molecules are useless. I would never bother with that. Can we do something with a wheel? We could build a bike. Let's stick with bikes. Let's go simple. We could build a bike. All right, so we could look at now an equation. What can we do now that we have this piece? All right, we look at this equation. We try and build a bike. So if you're going to explain to someone how to build a bicycle, what might you tell them? We need 2 wheels. All right, but that's you talking to them. What can we write down so that you don't have to talk to them? Because people are scary. There are 2 wheels for one frame. And we could write the 1 next to the frame. But do you want to go through and write that process out? Why not? It's unnecessary. It's already implied that there is 1. That's why we drew a pretty frame. Okay, so we can ignore the 1. We now have a balanced equation that someone could go through and use to build this bicycle. Okay? Which might be a nice bike, I don't know. So what can we do with this once we have that equation? Okay, here you got, what was it, 1, 2, 3, 4, 5 different conversions. Okay, work on these conversions with each other, see what you can come up with. You got questions, raise your hand, come to you. But when we look at our other equations, we end up looking at all these numbers and letters and freak out and say, oh my gosh, that's too impossible to understand. Okay? That's because it is really impossible to understand. That's why people have problems with chemistry. What you end up having to try and do is convert these units into something more understandable. So we're now taking those 3 species and we mash them all together and we make 1 species at the end. Okay? And what we're using is the coefficients, okay, the numbers in front, to allow us to generate the different relationships that we generated up here with building our bikes and frames. We have these conversion factors that allows us to convert through. So if we take a look at that first question, how many atoms of sodium are needed to make 1 molecule of sodium carbonate? Well, what's the formula of sodium carbonate? It's Na2CO3. So if I need to make 1 sodium carbonate, how many molecules of sodium do I need? Or atoms of sodium do I need? How do you know that? I need to convert into sodium atoms. What's the relationship? I need to get rid of the molecules of my sodium carbonate, and I need atoms of sodium. Where do I find that number? In the compound. It's in the formula. There are 2 sodium atoms in 1 sodium carbonate. So what answer do I get? 2 sodium atoms. Okay? The formula gave me that. I'm going to put the cap. Okay? If we switch that up and now say how many molecules of sodium carbonate are needed to make 2 molecules of sodium hydrogen carbonate. We again have another conversion factor that has to come out of this. What conversion factor do I need? I need the relationship between sodium carbonate, right, and sodium hydrogen carbonate. What is that relationship? How do you know it's 1 to 2? You look at the balanced equation, because that equation allows you to convert, just like our bicycle equation did, bikes into wheels, or wheels into bikes. If we look at this balanced equation, what does that allow us to convert? The thing that says sodium carbonate is this big, giant, massive, nasty-looking object that we now turn into whatever shape we want, into some other big, nasty object. The only thing I need out of that is the coefficient that shows up in front of them. I can now do the conversion. Okay? Kind of, sort of makes sense? So what you could go through and do is, instead of looking at those formulas, turn them into circles, squares, triangles. Okay? I need to convert. Jeez, it's the first time I've almost dropped that. Okay? I need to convert my circles into, oh gosh, I ran out of shapes. Stars. How do I convert circles into stars? Well, 1 circle becomes 2 stars. Do I care that the star has all of those other letters and numbers in it? No, it's completely irrelevant to what I'm trying to do. Okay? But before I can look at the number in front of my stars, what do I have to make sure is correct? That my star is correctly shaped. Right? It has to have the correct components within it. So we have to slowly work our way up to it, which is why when we go through and look at these, we have to balance our formulas when we predict our products. Once our formulas are correct, then we can balance the equation to get the numbers in front. Once we have the numbers in front, now we can build our conversion factors. Right? So it's lots of individual steps that add up and continue to build into this. All right? Should we do one of those later ones? Which later one do you want? Second or second to last? I mean last or second to last? Second to last. I like that one better. It's spaced to right. Okay, how many moles of sodium hydrogen carbonate are produced when 1 mole of sodium carbonate, water, and carbon dioxide are mixed? Okay, so what is that saying we're doing? We take 1 mole of sodium carbonate, 1 mole of water, 1 mole of CO2. How many moles of this are produced? Okay. So when we went back and looked at this calculation, to convert wheels into bikes, when we were given 3 wheels and 2 frames, what did we have to do? 2 separate calculations to determine if there's a limiting reagent. We now have 3 starting materials. So how many calculations do we have to do? 3. We'll convert sodium carbonate into sodium hydrogen carbonate. What's that conversion factor? I'm given 1 sodium carbonate, trying to convert it into sodium hydrogen carbonate. What's the conversion factor between those? For every 1 sodium hydrogen carbonate, I get 2, I think I said that backwards. Okay. What if I have 1 mole of H2O? Can I convert that into sodium hydrogen carbonate? I need to get rid of H2O, I need sodium hydrogen carbonate. Is there a relationship between those? I have 1 mole of CO2. What's that number? 2 to 1. Our answer in all of these cases, we get 2, 2, 2. So how many moles of sodium hydrogen carbonate do we end up with? I am fishing for that 6. What's wrong with 6? Could we add these? No. Can we add these? No. What are we looking for? Our limiting reagent, our smallest number. What is our smallest number? 2. What's our answer? 2. That's the most that we could make. We can't make any more than that because after that point, what happened to the amount of sodium hydrogen carbonate? It's all gone. I've used it up. So in this case, we don't really have a limiting reagent because we added everything in the perfect amounts. Okay. But what happens if we switch it up? Okay, we could go through and do the cheese and bread example. Okay, if we're trying to make a grilled cheese sandwich, you need 1 slice of cheese and 2 slices of bread. Okay, to make your 1 sandwich, what do you have to do? Well, we've got an equation. 1 slice of cheese, 2 slices of bread equals 1 sandwich. Right? If we now mess with this and look at what we have in our refrigerator, maybe we're a little bit hungrier than just 1 sandwich. Can we make more than 1 sandwich? We're setting up those conversions. We're setting up those equations and approaching this. And when we go through and look at this, if we have 5 slices of cheese and 8 slices of bread, how many sandwiches can we possibly make? Only 4. How do you go through and do that? 1 slices of cheese, or really, we don't have 1 slice of cheese. We have 5 slices of cheese. How many sandwiches can we make? Well, what's the relationship between cheese and sandwiches? Which means I could make how many sandwiches? 5. What happens if we look at our bread? How much bread do we have? 8 slices of bread. What's our relationship between our bread and our sandwiches? 2 bread to 1 sandwich, I get 4 sandwiches. So I can make 9 sandwiches. No. I run out of cheese. Right? Or bread, whatever it is. Run out of bread. Right? I stop at 4 sandwiches. I can't make any more than that. Okay, if you were at home, you probably didn't have to go through the math. You'd probably lay out all the bread, lay out all the cheese, and start making sandwiches. Oh, crap, I can only make 4. Okay? So if it's me, I can't have anybody over because there's no food. Okay? So we can't do that simple layout in front of us with chemistry. We have to look at those numbers and look at those conversion factors that allow us to do that. So we write it out so that we can set that relationship up. Okay? Oh, let's get out of the sandwich. So let's take a look at this one. 2 moles of sodium hydrogen carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced?
2.
Like we just went through and worked with, we have 3 reactions or 3 conversions that we've got to do. And I feel sorry for anybody that's listening to the recording because it's all written up on the board. How many moles of sodium carbonate do we start with? Okay. We're trying to convert this into sodium hydrogen carbonate, so we've got our conversion factor set up for us, which means how many sodium hydrogen carbonates can we make? 4. How many waters do we start with? How many sodium hydrogen carbonates can we produce?
4.
How many carbon dioxides do we start with? How many sodium hydrogen carbonates can we make? 2. What does that mean? The absolute most that we could make under these conditions is the one that generates the smallest number. So the most that we can make is 2 moles of sodium hydrogen carbonate. We're using the conversion factors to allow us to produce that. So what does that mean about our sodium carbonate in our water? We have leftovers. Okay? What do we do with the leftovers? Most typically we just throw it out. Kind of wasteful, but that's what we do. Okay? That's what's happening within our limiting reagent calculations. We have to go through and punch in all of those conversions to go through and process this. What happens when you move up into 151? It gets harder. What gets harder? I give you 2 grams of sodium hydrogen or sodium carbonate and 1 gram of water, 1 gram of carbon dioxide. How much sodium hydrogen carbonate can you produce? What does our balanced equation give us a relationship of? Moles, molecules. It's the number of a unit. It is not the mass. So if I give you grams of starting materials, what do you have to do? Convert it into moles. Once you're in moles, what can you do? Then you can set up your mole-mole conversion to get it into moles of your product. Your equation only allows you to convert moles or a number of molecules between each other. It says nothing about mass. All right, so if you're given mass, you have to convert to moles. So with most problems in 151, do everything you can to get your unit into moles, because moles allow you to convert through a balanced equation. We can then convert that species to something else. Same thing goes with this class. Do whatever you can to get it into moles. More than likely, you're getting closer towards your answer. Okay. Last thing I want to talk about, I know in the 30 seconds, we'll pick it up here on Thursday. Percent yields. Okay, if we go through and run an experiment, say let's build bicycles. Okay, you build 2 bikes, I build 16. Who's the better bike builder? I started with 32,000 wheels and 32,000 frames. You started, what did you guys get, 2 bikes? You started with 4 wheels and 2 bikes, or 2 frames. You're better at it. I could only build 16 out of 32,000 possibilities. You started with 2 possibilities and you made 2. Who's the better bike builder? You are. The raw number is useless. What we need to compare it to is what could theoretically have been made. with 32,000 frames, I should have been able to make 32,000. If I can only make 16, that's a bit of a problem. Right? So what we need to do is compare how much you actually got to what was theoretically possible. The theoretically possible comes back to our balanced equations. Theoretically, I should have gotten 2 moles of sodium hydrogen carbonate. Well, where do I get the actual yield? I do the experiment. If I do the experiment and I only get 1 mole, what's my percent yield? 50%. I actually obtained 1. Theoretically, I should have had 2. 1 over 2, 50%. Right? When we go through and deal with our units, they're unitless, so you got to make sure you use the exact same units in your percent yield. We will pick it up there, probably with that question. Yeah, we'll stick with that question.